So, hello and welcome back to another lecture on Introduction to Soft Matter. Today what we are going to do is we are going to look at some example problems. These example problems have been designed so that we can actually end up revising some of the materials that we have been discussing. So, it will be a very good work through some of the important concepts that we have already discussed, right. So, we have a few different problems to explore today. But the first problem that I have designed. So, we want to take a look at a certain type of viscoelastic material for which the analog is already given to you. Okay. So, let us say the problem 1. So, the problem 1 is a Jeffreys fluid element. And if you recall, the Jeffreys fluid element comprises of a spring and a dashpot in parallel, and then another dashpot that comes in series, right. And what we are given is the values for the moduli here that we will use are given to you. So, here the spring is characterized by E, which is given as, let us say, 300 pascals. The viscosity here is given as 5. Okay. And this is another viscosity. So, this is given as 1 pascals. So, we see that we have these two different dashpots, and the numerical value or the strength of these dashpots are different values, right. And the question is, so the question we are trying to ask is, find out the expressions for GT and JT. By this time we are very well familiar with what JT, these two GT and JT imply, right. So, we are not writing the full form, we are just going with the mathematical form that we have already, we are quite familiar with at this time. Okay. So, now let us try to solve this particular problem. Now, this is the constitutive equation for this will be the constitutive equation for a Jeffreys element, and we have already seen that in one of our class. We have already worked that out. So, we are not going to repeat ourselves. So, we are just going to take that result, right. So, the constitutive relationship for this for the Jeffreys element I think this is not apostrophe. Jeffreys element is already well known and we have derived it earlier. So, if we just recollect from our memory, or you can take a look at your notes, you will find that the constitutive relationship for this is given as, on this side we will have the derivatives of stress and its higher derivatives, and on the other side of the equation we will have strain. So, here we have P1 into the first time derivative of stress plus another quantity P naught, where P1 P naught are coefficients for this differential equation, and on this side we have the double derivative of strain. So, I am going to write Q2 here and Q1 epsilon dot, and we already also know that these coefficients can be expressed in terms of the variables that comprise the Jeffreys element. So, these 4 coefficients here can already be expressed in the terms of these 3 variables that we have. So, P1 is equal to eta plus eta 1, P naught is equal to E, Q2 is equal to eta into eta 1, and Q1 is eta 1 times E. Okay. So, these 4 coefficients are well known. Now, we have to solve this particular differential equation. Okay. So, let us take the Laplace of both sides. Okay. So, to solve this, let us apply Laplace transforms. Okay. So, and we are going to use the same convention that we have used before. So, for example, if you have sigma, then sigma bar s basically tells you that is a Laplace transform form, and s is the variable that corresponds to the Laplace transform, right. So, we can write, we have P 1, here we will have S sigma bar S minus plus P naught. Here there is no derivative. So, this will just simply give us sigma bar S. So, as I said before, this bar implies a transform, and S is the variable for the Laplace transform. And then you have Q 2, and here you will have S square epsilon, sorry. So, you have epsilon bar S minus S times epsilon 0 plus minus epsilon. So, this is the expression for the first term, and then you have the second term, which will give us Q 1 times S of epsilon bar S minus epsilon. So, now we have this Laplace transform. The problem with this particular equation is now we have these variables for which we need to know the answers for, and this should come from the compatibility conditions. Now, the compatibility conditions or the initial conditions for this can be derived from the repeated application of the integral formulation that we had looked at before. In this particular case, it becomes a little bit tedious. So, I am just straight up going to tell you what the answers will be. What will happen is, when you derive that all these values will just drop out. So, these will all drop out, okay, which will leave us with only the first terms for this that are involved here. So, this equation now will become plus P naught right. So, as I said, we have skipped one part where we show how these terms drop out, but basically they can be derived from looking at that limiting process that we have seen before. And once you apply that and the initial values and the stresses that are evaluated at these particular at 0 plus the values of the stress and the strain and the derivatives, then you see that they will actually drop out of this transformed equation. Okay. So, now we can write our equation as on this side we have epsilon bar S, you have Q 2 into S square plus Q 1 times of S, right. So, to get the functional forms for G t or J t, we have to solve this equation using the appropriate condition, right. If you are looking at the stress relaxation function, then our epsilon or the strain is a step function, right. If it is a step function, then we know that to evaluate G t, we have to set epsilon t as being equal to epsilon naught into the Heaviside function, right, which implies that epsilon bar s in that case will simply be epsilon naught by s. Okay. So, now if we substitute this value into this equation for sigma bar, we have this particular equation q 2 s square plus q 1 s into epsilon naught will be in the numerator. In the denominator, we have s multiplied by p 1 s plus p naught. Right. Okay. So, this obvious there is an extra s here, there is an s here and there is an extra s on the numerator. So, this will actually simplify down to epsilon naught q 2 s plus q 1 divided by p 1 s plus p 0. We are already familiar with how to solve such equations where such fractional forms are there, right. So, let us go ahead and try to solve this. So, I am a bit out of space there. So, I am just going to write it over here. I am just going to simplify my expression a little bit and make it such that the numerator has an s plus p naught plus p 1, and in the this is sorry, I am going to simplify the equation a little bit. So, that I divide the denominator by p 1, I end up with s plus p naught by p 1. In the numerator, I divide by q 2. So, I end up with s plus q 1 by q 2, and hence I have to multiply on this side to balance everything out q 2 into p 1. Okay. So, this will now give me, let us say, so I am going to just this constants I am just going to club together into 1, and now I have this particular partial fraction form to solve. So, I can write this as, my assertion is I can write this as 1 plus p naught by p 1. I here in the numerator I will have okay. See, I deliberately did this, right, because when I have to take the Laplace inverse, I have to take the Laplace, this is a constant, here this is just 1, and here this is a functional form that we are well acquainted with. So, we already know what the Laplace inverse of this is, right. This will be an exponential form, and the Laplace inverse for 1 will be the Dirac delta function. Okay. So, when you take the Laplace inverse, so now this was my, this is still in the Laplace domain. So, this is my sigma bar s. Now, to solve this I have to take the Laplace inverse. So, taking the Laplace inverse, once we take the Laplace inverse, we can go back into the time domain. So, now when we do the Laplace inverse, I will get sigma t. So, it is a function of our time, and on this side we are going to take the Laplace inverse of this entire thing. Now, this is a constant. So, we can just leave it as that. We have epsilon naught q 2 by q 1. Okay. And here we have to take the Laplace inverse of 1, that will give me the Dirac delta function plus the Laplace inverse of this, sorry, this will be q 1 by q 2 minus p 0 by p 1. This is my multiplier, and here we have the exponential form, which will be just minus p 0 by p 1 t. Okay. So, from here to go to j t is just one more step. right. So, I just divide this sigma t by epsilon naught to arrive that is my g t function, and that can be written as q 2 by q 1 delta function plus this entire thing remains the same. Now, we have the expression, this is what we are looking for. So, by the way, this is at least the answer, or at least part of the answer. We will evaluate this numerically also, but this is the algebraic form that we were looking for. Now, whenever you do a calculation like this, it can sometimes become tedious, as you saw that we have a lot of Laplace transforms. We had to take the Laplace transforms, then we had to take the Laplace inverse, and this often a scope for silly mistakes. So, you might end up missing a term, or you take the incorrect Laplace inverse. So, I mean, usually my rule of thumb is whenever you do a calculation like this, then one thing you should do is just subject it to a sanity check, right. So, the question is, now that you have this answer, I mean, can we do a simple sanity check to see whether this form is anywhere close to a real form that should be there. Now, for that, let us just quickly go back to the Jeffreys element. Now, this is going to act like a fluid element, right. Because we have discussed this part already when we are discussing Jeffreys fluid, that this is essentially should be representing the constitutive equation for a viscoelastic fluid. So, we expect a fluid like behavior. So, we also expect the function of the stress relaxation function to behave as if the material is a viscoelastic fluid. What happens in a viscoelastic fluid? The stress relaxation function should decay to 0 at large times. Does this decay to 0? Yes, you can see this is a Dirac delta function, and then you have a term that is exponentially decaying with time. So, this entire form is going to go over to 0. So, this does qualify through our simple sanity check that this form is indeed looks at least correct, and if we have done the algebra right, then this form is the algebraic expression is exact. One more thing, you see that this strange Dirac delta function is there, right, and what is the physical reason for that? The physical reason for that actually comes from the fact that this is actually a fluid element. Okay. So, when you have to give a step function, so if you give epsilon naught into h t, to get to that initial value of strain, you need a very high jump in stress, so that these dampeners can quickly instantaneously go to a finite value of strain, and that is what actually causes this kind of a problem. So, you can see that although we have derived the expression, there is slight non-physicality in a sense that exists in the relationship. Okay. So, we have all the values for q 2, q 1 etc. So, we can just simply go ahead and evaluate that. So, now that we have the expression for g t, what I did, I realized that there is a small error, and it happened midway somewhere, and this here it should be p 1. So, this value should be p 1. Okay. Delete the whole thing. Okay. So, now this is the correct expression for g t. Now, we already know the numerical values for q 2, p 1, p naught, p 1 etc. right. So, all the 4 coefficients we already know what the numerical values will be. So, if you take those numerical values, so using the numerical values for p 1, p 0, q 2 and q 1, we will get this g t as, okay, so this is the result that I got, and you are please invited to do this by yourself and check whether my expression is correct or not. We have 300 here, it is 300 by 6 e to the power minus 300 by 6 t, right. So, this can be simplified a bit more. This will give us 10. So, and this is basically 50. So, my final expression for GT would be 5 by 6 delta t plus 25 by 3 e to the power minus 50 t. Okay. So, this is the final answer in numerical form that we are looking for. And as I said, you are free to do this calculation by yourself and check my answer. Okay. So, when we started out, we had two questions. We had we wanted to find out the expressions for GT and the JT. So, let us go ahead and try to see how JT will look like now. So, for creep compliance, the relationship between the original transform equation remains the same, right. So, it is P1 S plus P naught, and on this side you have epsilon bar S Q2 S square plus Q1 S, right. And for creep compliance, now the quantity that is known is the Laplace transform of sigma bar, or the Laplace transform of the stress function. So, the Laplace transform of the stress function is simply some sigma naught by S, right. So, this implies that epsilon bar S is equal to sigma naught by S multiplied by, here you have S plus P naught by P 1. I am just simplifying the numerator a bit. You have S square plus Q 1 by Q 2 S, and since I have divided the numerator by P 1, I am just going to multiply here by P 1, and here we will have Q 2. Right. So, this Laplace transform is interesting because now you have this interesting x square. So, the numerator the denominator now has certain higher powers of the Laplace variable. So, this will now become, so if I just club all the constants together, so sorry, this is Q 2. And in the first, so I am just going to split this into two partial fractions here, and here we will have, so this S will get cancelled with this one. So, we will have an extra S here, S plus Q 1 by Q 2, and on this side we have P naught by P 1, we have S square S plus Q 1, right. So, this is an interesting problem now, because this Laplace transform is slightly different than the one we have seen before. So, I encourage you to do this problem by yourself. Right now, it is basically going to be very similar to what we have, the process we have adopted before, but it is a very good exercise to try it yourself. So, what I am going to do is, I have the answer written down from my calculations, and I will just write it down, and I encourage you very strongly to go through this by yourself and double check, right. Okay. So, I am going to write down the expression I got. So, the expression that I found is Jt is equal to, so I am just writing it down, the final form is P naught by P 1 times T. So, there is a linear part to it, and then there is P 1 by Q 1 minus P naught Q 2 by Q 1 square 1 minus e to the power minus Q 1 by Q 2 t. So, this is the algebraic form. Okay. If this is maybe a little bit difficult to read, I will just write it again. This is Q 2. Okay. So, if you again insert the numerical values that we have seen before, or for these coefficients, then you end up with this final expression 1 minus e to the power minus 60 t. Okay. So, this is our final expression. Now, please notice a few things here, and that the creep compliance function has a linear part and there is a decay part. So, this function seems to be far more well behaved than the one than the function Gt, right. But notice the powers of the exponential function. Here it is minus 60 t, and for the stress relaxation function it is minus 50. So, the two values are different. So, we have two characteristic time scales corresponding to the two different functions that we have explored, right. And one is we know as the relaxation time scale. So, with the characteristic time scale there associated with Gt is the relaxation time scale, whereas the one that is associated with the creep function, that is the retardation time scale, right. Okay. So, this was our problem 1. Let us take a look at another problem. Okay. So, problem number 2. So, we will end today's lecture here, and I will see you in the next class. Okay. Thank you.